So good morning, everyone. And I am going to, this talk is going to be slightly different as compared to, I attended Professor Gokan's talk in the morning just to sort of get an idea also of what was being discussed and the kind of audience. But this is going to be slightly quite different from what perhaps you will be listening to in the course of this workshop. I am not going to talk specifically about Earth system models. There are enough experts in the field who are going to talk to you about it over the next few days. I'm going to focus my attention on integrated assessment models, which are used. Outputs from these models are used as inputs to ESMs, at least for some aspects. And there is, of course, outputs from the ESMs that are also used in order to run scenarios in the integrated assessment models. While some of the issues of model resolution, setting boundary conditions, or approximations are similar to the Earth system models, and of course, the conceptualization of the integrated assessment models is, derives from the ESMs. Nevertheless, a lot of these issues are normative in nature. Unlike physical system boundaries, here system boundaries are economic in nature. Sorry?
Are you changing your slides? Because
not yet. Okay. Okay. So, here system boundaries are normative in nature. They are, economic conditions that are set. So I am going to talk about some of these issues and maybe end with a question of whether the question here in the IAMs is, do we need better data? Do we need better model fits? Do we need better training of data? Do we need to use more novel methods for data training? Or do we simply need better models? And by that, I mean, do we need better approaches to modeling itself? Given that you're modeling a very different system here, it is not really it's very different from modeling Earth systems. So let me begin by, I'm not sure how familiar you are with integrated assessment models per se, but let me begin with a brief introduction. So integrated assessment models are basically, as the name suggests, they are integrated models of economic systems, earth systems, energy systems. So there are multiple modules and the idea is to evaluate a lot of this together so that you can assess mitigation policies, policies for climate change mitigation, policies for climate change adaptation, how these interact and so on. So earth system models, for example, use certain kinds of forcings. You use use forcings for different greenhouse gases or land use and other kinds of feedbacks. And a lot of these are, of course, a result of economic activity, a result of human activity. So that how that human activity is going to pan out in the future also needs to be modeled because there are drivers. Why would you have a certain kind of emissions outcome? But that then you need to check the impacts of, or you need to check what kind of systemic changes it causes in different in the atmosphere or in the ocean or on land. But how is it that the drivers themselves also change? So in the IAMs, what you have broadly, it consists of macroeconomic models, and these are traditionally, macroeconomic models have been used for many years now in the realm of economic planning, also to try and understand how economy. In the context of climate change, of course, they are now being used to also model long-term futures. They're not necessarily meant to do this because you think of things like GDP, economic output, economic activity. These are not things that you can model over long time horizons because there's too much dynamism in the way things happen. There is, small policy changes can have significant impacts on economic activity. You take something like demonetization or the introduction of the GST in the Indian economy. And that's one policy change, and you have significant impacts on economic activity. So imagine this on the global scale and with global interactions in trade and things like that. So when there are increasing trade tariffs, for example, there is going to be impact on economic activity. So how all of this changes is very, very dynamic. And nobody would have, for example, none of the models that were built 5 years ago or even 2 years ago included sort of scenarios for determining what's going to happen if you have large-scale tariff barriers that currently, for example, like the United States is putting up against other countries. So what happens when something like that happens? Right? How does it impact trade? How does it impact the possibility of transitions out of fossil fuels or other such related issues? So macroeconomic models were traditionally meant for short-term understanding, and even then there are a lot of assumptions embedded in these. But now, of course, because for climate change and temperature feedbacks, you're looking at long time horizons. This is what is required by Earth system models as an input. An input of 2 years or 3 years or even 5 years of emissions is of no use. You need long-term trajectories that will allow you to model forcing, and the impact of emissions increase, let's say, on temperature or other Earth systems. So macroeconomic models, the same variety of them, have now been used for this kind of long-term modeling. You then have, these are coupled to energy models. Now, energy is an important aspect because a large majority of greenhouse gas emissions is coming from the industrial and fossil fuel sector, especially carbon dioxide. So this has been a large part of energy emissions modeling from the beginning of the discipline per se. But again, energy models have been used in the energy sector for a much longer period of time. Not necessarily only to address questions of climate, but also address issues of costs. How is it that you optimize resource use? Some regions only have, let's say, coal. Others have oil and gas. There is a need for export and trade between these different energy systems. There are certain requirements of power grids and so on and so forth. So you have energy system models that have been used traditionally for a long period of time for energy sector planning. Of course, now in the larger scheme of things, I apologize. In the larger scheme of things, there is this is again now long-term planning that we are, or long-term projections that we are talking about. Vegetation models have been part of some of these modeling exercises for some time, but they have become increasingly more important and prominent in more recent times. Of course, also because we all know that the amount of carbon budget available for limiting warming to 1.5 degrees Celsius is almost exhausted. 1.5, of course, we discuss details of it if necessary at some later point in this talk. But you need the land sector, of course, both as a carbon sink as well as for the provision of other kinds of options, especially in terms of energy. Bioenergy, for example, plays a major role in the carbon cycle in general. But here it is also becomes important as a sector for mitigation of climate change, not just sort of as one player in the larger carbon cycle, but as an active contributor to mitigation. And these dynamics need to be modeled alongside the dynamics in the energy sector and the economy as a whole. And all of this, of course, is then, there is also Earth system feedback to which it is coupled. There are emulators that are used, not necessarily large ESMs, because this is, computationally far more complex to do. So Earth system models typically will use a smaller subset of forcings, greenhouse gas emissions forcings that come from these IAMs, and do a larger ensemble of model scenarios on those. But IAMs themselves then take Earth system feedback. So if you look at the total cumulative emissions that are implied by certain trajectories that correspond to certain temperature targets, then you use those as constraints in the IAMs to look at what are the possibilities for energy sector transitions or transitions in other sectors, mitigation options in other sectors in the IAM. So the way in which this has developed over a period of time, the IAMs had a sort of a limited role of providing these kinds of at least the emissions trajectories to the Earth system models at an earlier point of time. However, there has been increasing focus. Of course, in the arena of climate policy is no longer necessarily only about convincing people that climate change is real. That was the burden of the story for a few years when the conversations around this started. The last few years, some exceptions notwithstanding, the last few years, however, have been about how is it that you address the issue of climate change. So aspects of socio-economic projections, looking at what are the drivers of energy use, fossil fuel emissions, etc., into the future, have become much more important. So then the way in which this developed, I won't get into the history of it, but in the 6th assessment report of the IPCC, what was used was a sort of a combined SSP-RCP combination. The SSP stands for Shared Socio-Economic Pathways. RCP are Representative Concentration Pathways. So how is it that you combine these two to arrive at certain scenario storylines? And these are baselines over which then mitigation policies are modeled. So how does the baseline is supposed to give you narratives about how the world develops. Now, if you just look at these questions, you realize how normative in nature these are. You're not talking about how, warming, surface ocean warming is different as compared to, other aspects of, deep ocean or some other physical system conditions where there are, of course, uncertainties even in those systems, but you can at least, to a certain extent, fix those uncertainties. The uncertainties themselves are knowable. Whereas on the other hand, in economic systems, the uncertainties themselves cannot be fixed in any particular manner. So the baseline talks about how the world develops and what is the adaptation and mitigation effort at different temperature levels in this world. So there were 5 different shared socio-economic pathways or narratives that were developed as part, and these were used broadly as in the 6th assessment cycle of the IPCC, which is the Intergovernmental Panel on Climate Change. So SSP1 was sustainable and inclusive development. This narrative talks about the fact that there is cooperation across different regions. The focus is on sustainable development, inclusive development, reducing inequity, and so on and so forth. SSP5 is fossil fuel development. So if you look at the baselines here, there is larger growth because a lot of it is also driven by larger resource extraction over the entire century. And then there are other SSPs which are in the middle. SSP2 is middle of the road, which follows broadly what is called business as usual. So trends of the major drivers, the trends of the past continue more or less into the future. This kind of, the SSP2 kind of narrative is more given to sort of better, where you focus on model validation, data training, and so on, because you want to be able to reproduce past trends into the future. But if you look at the narratives themselves, none of them necessarily are only reproducing the past into the future. The entire point of being able to deal with or address the problem of climate change is to actually break from the past. And so your trends and projections are necessarily doing something different in the future that it was not done or has not been possible or simply did not happen in the past. So SSP2 is business as usual. SSP3 is regional rivalry, which means that there are barriers for trade that are set up. So in this particular SSP, the way in which they define regional rivalry is that countries have more protectionist attitudes, they will not cooperate with other regions, and so on and so forth. And SSP4 is a narrative that focuses on inequality. Now, this gives you a sort of a feeling that the other, because you have a specific narrative that focuses on inequality, the other narratives are more or less focused on equality. That is not true. I will speak about this as we go on. So you have basically all of this run together in the integrated assessment models. So what you have is are global outcomes, which are spatially and temporally optimal. They are driven by these storylines. So within each storyline, you have multiple scenarios that are possible for mitigation, emissions reduction, which sector plays a bigger role in emissions reductions, and so on and so forth. So in the AR6 working group 3, I'm not sure if you're familiar with the setup of the IPCC. Working group 3 focuses on mitigation. Working group 1 is where a lot of the Earth system modeling stuff really is assessed, and that work is undertaken. So that is the physical science basis. Working group 2 focuses on adaptation, vulnerability, impacts, vulnerability, and adaptation. Working group 3 is climate change mitigation. So mitigation is where a lot of the climate policy, fossil fuel transitions, etc., all of those most contentious things are really discussed. So the working group 3 gave a call. The authors basically gave a call for the submission of global scenarios. About 2,425 scenarios were submitted, but modeling teams, especially the ones that look at energy, economy kind of modeling, have for long focused on shorter term projections because these are much more reasonable. You can, you can explain them better. You can also have some kind of feasibility assessments, whether or not it is possible to get rid of coal. How soon can you get rid of coal in, let's say, India and China? How soon can you phase out oil use across the world? So, there are, of course, feasibility issues involved here. How much can you integrate renewable energy into the grid, etc.? So if you do this for a shorter term, you can assess feasibility far more realistically. Whereas for the long term, it becomes far more difficult. But if you have only short-term scenarios, you cannot assign a climate assessment because you cannot say that these are 1.5, 2 degrees, 3 degrees, 4 degrees, whatever compatible. So you can't assess a temperature level that corresponds to those scenarios. So only 1,594 were assigned a climate assessment, and of which, again, 1,202 passed the vetting criteria. Now, this is unlike model, scenario ensembles that we talk about in the Earth system models, where you are running a whole, you keep certain variables constant and you run a whole range of scenarios. It allows you to fix uncertainties, allows you to compute probabilities, and so on and so forth. Here, of course, this is not a statistical sample of any kind. This is model scenarios submitted by a whole bunch of modeling teams across the world. Each of them have a different criteria, a different model, a different approach, possibly. So about 1,202 scenarios do not, while it sounds like a large number of scenarios, it's not really a statistical sample. So you can't, it doesn't mean much to compute a mean or a median or anything from these scenarios, because simply if you have one particular modeling team submitting a large number of scenarios, and this is exactly what happened, the results from that particular modeling team or that particular model are going to dominate any kind of statistical parameter or statistical means or medians that you estimate. So of this 1,202, about 700 correspond to the 1.5 or 2 degrees Celsius temperature range, which are basically the Paris Agreement temperature goal range. Of these, about 556 have a 10 region classification. Now, it's important to understand that while these are global scenarios, they all have an underlying regional distribution. It's not as if you do an optimization at the global level. You do a global optimization, but it optimizes across regions. And there are certain assumptions that are embedded in this entire, the way in which these models are structured. So you can have, how is the world divided in these models? So you have, it's basically divided by regions, not by developmental groups or so on and so forth, but by geographical regions. And you can do this. So there are models that have 5 region or 6 region. So basically continents are regions. But if you have all of Asia together, then of course China dominates the rest of the continent, all of the Americas together. So it doesn't really help you to do an analysis to use the 6 region classification. So 10 region classification allows for an assessment of what these outcomes are, at least in terms of whether or not these outcomes are equitable or not, a little more easily. So then you have a whole range of variables. Now, it is also important to remember that because there are about 21 different models from which these come, and each of these models have a different set of variables that are either endogenous or exogenous, or in some GDPs, endogenous, for example, to the model. It's endogenously computed. In others, it is semi-endogenous, which means that while it is computed endogenously, it is still vetted against some kind of an external trend, GDP trend. And if the mismatch is too much, then you have to do another iteration of the runs. And then there are, of course, other CO2 is typically an outcome of most of these models. Energy consumption is optimized differently across different models and so on and so forth. But if you look at some of the headline statements that you might have read coming from the 6th assessment report of the IPCC, these were about that the world needs to do a 43% reduction in emissions by 2030, 60% reductions in 2035. So irrespective of whether the variables are endogenous or exogenous or so on and so forth, together they describe the world or, in the future, they describe the future. And this future then, as normative as it is considered, because it comes out of mathematical models, is considered to be scientifically determined, and then these become de facto targets. Of these 556, 354 have an integrated land use component, and so you can also determine things like food demand, food prices, populations at risk of hunger, etc., etc. And these become important in the kind of analysis that is there done. Okay. Of the scenarios that were submitted, a large number, forget a large number, in fact, most of them were SSP2, business as usual kind of scenarios. The inclusive sustainable development scenarios were very few. And if you actually look at the differences between SSP1 and SSP2, for most regions, the differences are very, very small because the models don't allow changes beyond a certain point. We'll talk about this briefly as we go along. So there were 4 scenario categories, and I'm going to briefly, before I go into why we, what are some of the issues involved here, I will talk about some of the outcomes of the models themselves to give you a flavor of why this is an issue of concern. So we looked at these 700, about 556, not 700, 556 trajectories that have an underlying 10 region classification and 4 different temperature targets. So you have 1.5 degrees Celsius with the likelihood of 50% or greater. But this is with no or limited overshoot. C2 is with overshoot, again 50% probability of 1.5. C3 category scenarios, which had the most number of scenarios, at a 67% probability of 2 degrees Celsius, so of limiting warming to 2 degrees Celsius, and then a 50-50 chance of 2 degrees Celsius, another 125 scenarios. You look at the 10 region classification of these, Annex 1, which is the developed countries as per the United Nations Framework Convention on Climate Change, UNFCCC classification. 18% of the global population is in Annex 1 regions. This consists of North America, Western Europe. Reforming economies are economies of the former Soviet Union. So they're called economies in transition, reforming economies. There are various terms that are used. And the Pacific OECD, which is basically Japan, Australia, New Zealand. So these are developed countries, which are Annex 1 countries. Non-Annex 1 countries with 82% of the global population are basically covered by the other regions, Sub-Saharan Africa, Southern Asia. So this is actually, there are some models that look at Sub-Saharan Africa separately, some that look at Africa as a whole. Southern Asia is basically India and the Indian subcontinent. China plus is China plus a couple of other countries, Latin America, the Middle East, and the rest of Asia. There's of course also the rest of the world, which is again a minor set of countries that are not covered by these categories. We looked at some of the outcomes of some key variables across income, energy, and emissions, and we found that scenarios assessed by the IPCC project continued global inequality across all variables. And some of this is pretty stark. So if you look at C1 scenarios, which are the, if you remember, 1.5 degrees Celsius scenarios, 50% probability of limiting warming to 1.5 with no or limited overshoot. Then these are the projections that you see in per capita GDP between 2020 and 2050. So Sub-Saharan Africa goes from about $3,000 to $9,000. So the current global average is about $15,000, $14,000 to $15,000. So they are below the global average currently. They remain below. South Asia is below today. It goes just above, but the global average in 2050 is much above 15,000. I think it goes up to around 24,000. But South Asia remains below the global average even in 2050. So does the rest of Asia. The Middle East does reaches above the global average. Latin America, again, just above the global average, and so on and so forth. China does all right. But if you look at Western Europe, Pacific, OECD, and North America, from already high levels of GDP, they go to even higher levels of GDP. So your divergence between the developed and developing countries continues to remain. This is true even in the 2 degrees Celsius scenarios. The C3 scenarios are 67% probability of limiting warming to 2 degrees Celsius. If you look at the GDP projections, they don't really differ much. So the economic output remains more or less constant across both sets of scenarios, irrespective of what warming level you are looking at. GDP growth for most of these scenarios is constrained in developing countries in most of these. The outcomes are even more stark if you look at other variables of economic activity. So one other variable is the per capita consumption of goods and services. This is a component of GDP. Here it is even more stark. Sub-Saharan Africa goes from 1,000 to 3,000. South Asia goes from 1,000 to 4,000, and so on. And the developed countries, Annex 1 countries, if you don't consider the reforming economies, which is basically Eastern Europe, Russia, and the rest of Eastern Europe, the Western Europe, Pacific, OECD, and North America go from already high levels of consumption to much higher levels of consumption. And again, this doesn't change much at all, even in the 2 degrees Celsius scenario. Only marginal differences in the 2 degrees Celsius scenarios. This is coupled very directly with energy consumption in the outcomes for energy consumption. So primary energy consumption is very strongly correlated and remains correlated with economic activity. So if economic activity is low, then primary energy consumption also remains low. And so primary energy consumption is constrained to a very, very low level for Sub-Saharan Africa and South Asia. If you look at the last two bars here, that's basically Sub-Saharan Africa and South Asia. So energy consumption disparities remain. Sub-Saharan Africa remains at around 20 gigajoules per person. This is how much India consumes right now. 20 to 23 gigajoules per person. North America is the highest at about 160 gigajoules. They're about 200 currently. They do reduce a little bit and they reduce to 200. So this is not just fossil fuel consumption. This is energy consumption itself that is restricted. Fossil fuel consumption in per capita terms also continues to remain higher in developed countries. So North America, for example, continues to consume more fossil fuels as compared to developing countries. Now, this is if you're even a little aware of some amount of climate politics, the entire question of equity is very important in climate change negotiations that happen under the United Nations. The ICJ, for example, is going to give an advisory opinion. It's going to come out on the 23rd of July. There was a big case that was happening currently, and equity is a major issue there, the right to development. And this is very much embedded as a principle, both in the UNFCCC as well as its instrument, which is the Paris Agreement. The principle of equity is very much embedded. And so, which means that and it is also translated. If you look at the language of the United Nations Framework Convention, it is very, very clear that the interpretation of equity is that developed countries have to take the lead. Now, this is far from developed countries actually taking the lead. And if you look at C1 to C4 scenarios, so there is slightly more space, more carbon budget available in the 2 degrees Celsius scenarios, but that space is afforded to developed countries. So, their effort becomes slightly lesser in the 2 degrees Celsius scenarios. It's not as if that higher carbon budget space is actually then afforded to developing countries. So, all of this is interlinked. This is linked to fossil fuel use, continued, use of fossil fuels in developed countries. So I'm going to skip through some of this. And this sort of higher mitigation, higher amounts of fossil fuel use in developed countries is counterbalanced by higher land-based mitigation in developing regions. Now, land-based mitigation is basically carbon dioxide removal. It's either carbon dioxide removal through carbon capture and sequestration or through land use, which is basically afforestation, reforestation, and reduced deforestation. So you have large amounts of carbon space that is artificially created in some of these scenarios by assuming large amounts of carbon dioxide removal. And this is where the vegetation models come into play. They become really important. And they feed these vegetation models actually feed directly into land use scenarios are developed in the IAMs and fed directly into the Earth system models. So all of the assumptions of how land use will change. And you ask anybody, you don't need to be an expert in climate, you don't need to be an expert in energy or an expert in land. If you ask anybody whether the question of land is non-normative in nature, is it simply a scientific question, or is it it's a highly political and economic question? Anybody, even a layperson on the street will tell you land, of course, is at the very outset, from the very outset, is a highly political question. So a lot of this is used directly in the Earth system models. So when we use outputs of Earth system models or the model runs of Earth system models as sacrosanct or as scientific output, one must also remember that some of the inputs, at least, if not all of them, are also normative in nature. They are not completely value neutral in some sense. So if you look at what if you look at how carbon dioxide removal is modeled in these scenarios, so this is the Annex 1, developed countries, so North America, Pacific OECD, Western Europe, and reforming economies. So they do about less than a quarter of total carbon dioxide removal in the scenarios. This is by models. So this is from the Message-IX Globiome model. The Middle East does a whole lot in terms of carbon capture and sequestration, but not too much on land. If you look at China, China has to do quite a, China plus has to do quite a bit, both in terms of land and CCS. The rest of Asia has to do a whole lot in the land sector. Latin America, again, that's where the Amazon is, so has to focus a lot on sequestration from forests. South Asia has to do a whole lot on CCS, and a large amount of the CCS is actually bioenergy capture, carbon capture and storage. So that is what is called BECCS. So large amounts of land for food crops is then diverted for land for energy crops and so on. So this is true across all models. You see much higher levels of carbon dioxide removal in developing countries as compared to developed countries. And this is, of course, there are key concerns here. One is whether or not sequestration itself will remain effective with increasing warming. And you really don't have, a lot of this modeling does not take into account the impacts of climate change itself. Okay? There are socio-economic barriers in implementation of such kind of land use measures. If there are implications for livelihoods. It's not as if we have forests devoid of people. In most parts of the global south, forests are also places where people live and depend on forests for their livelihoods. There are impacts on indigenous communities, their potential to delay or deter fossil fuel emissions reductions as well. And this is very clearly a trade-off in the integrated assessment models. A lot of the more stringent mitigation scenarios lead to increasing food insecurity, and a significant increase in the number of people at risk of hunger under the stringent mitigation pathways. Okay. And a lot of this happens, like I said, one is you have diversion of land for energy crops, or there is competition for land. So the way in which the land sector is modeled is also through optimization. A lot of these models are optimization. What do you optimize in the land sector? You optimize the total revenue. So you maximize the revenue that you get from land. So if the land gives you more revenue for, let's say, you have a higher carbon price and you're sequestering more through forests, then that will give you more revenue. So if you have agricultural land, it will be much more beneficial economically for you to convert that land to forestry, because that will give you more money. Whether or not that has implications for food security is a different thing altogether. And so, once you have this competition for land that is included, it also means higher food prices. And these food prices then end up suppressing the demand itself for food, which leads to the higher risk of hunger, especially in South Asia and Sub-Saharan Africa. So, all of this together leads to much higher burdens for mitigation in Sub-Saharan Africa and Latin America. In developing countries, basically have much higher burdens, contravening directly what I said earlier is enshrined in the UNFCCC. So what I will focus on a little bit now is why do these models give these kinds of projections. One is, of course, the underlying philosophy of the models themselves, the underlying normative approach that is used. And the broader idea is one of Pareto optimality, which is you try and find an optimal, and this is across all different models. I spoke about land. In the economic sector, in the economic module, what you're optimizing or maximizing is welfare. How do you define welfare? Welfare is defined as a sort of a combined global welfare, that is combined utility in each region. But if you try and do this, then you'll have much more rapid increases in income in developing countries, and you'll have more or less an attempt to at least equalize incomes across different regions so that you are able to achieve universal well-being. But this is not allowed by the models because there's a normative assumption, normative approach of the modelers that considers this to be unreasonable. The equalization of incomes is unreasonable, is unrealistic. And so what is used in some of the models at least is what are called Negishi weights or the Negishi framework, which allows you to achieve Pareto optimals. Pareto optimals is one particular interpretation of welfare. And that is, if you have to make somebody better off, the overall wealth has to increase. So you cannot make somebody better off by making somebody else worse off. So there can be no distributive justice in this entire system. So you have to implement some kind of trickle down. So unless the rich get richer, the poor cannot get less poor. So you can't make the poor a little better off by making the rich a little less rich. That's not allowed by the modeling philosophy itself. There are, of course, other normative assumptions. One is, of course, that you have to assume a perfect market. These are stylized scenarios. So any kind of subsidies, taxes, etc., are considered to be distortions. And these are then implemented on top of existing economic assumptions and they say, okay, if you have a policy of carbon taxation, what happens? If you have a policy of subsidization, what happens, etc. You also have different kinds of trade-offs that are also normative in nature that are implemented in the models. Of course, one is, you vet for GDP. You can't have GDP growths that are unreasonable. Right? So like I said, the 1,202 scenarios that eventually you ended up getting were vetted scenarios. Vetted means that they more or less conform to GDP projections as they were. Population projections are not too off the mark. Urbanization assumptions are not too off the mark from historical trends or from what is considered to be valid, plus or minus 20%, etc., etc. So there are different bounds given for reasonableness for different variables. Now, so you have a lot of this is, so some of these variables are vetted for reasonableness, but you have no vetting of technology. So the large-scale deployment of negative emissions technologies, that is what NETs mean, in a lot of these models, whether this is actually feasible or not is not examined in detail. What kind of implications does it have for food security? And will it be possible for governments to implement these kinds of mitigation measures while ignoring a lot of the other developmental imperatives that they have? There are unprecedented rates of energy transitions that are assumed in the poorest parts of the world. Can Africa and South Asia, given where they are currently, given the kind of resources they have, their per capita incomes, and the low levels of energy consumption, is it possible for them to leapfrog to renewable energy and alongside also meet their requirements of modernization, industrialization, etc.? Or is it assumed in the models that these regions will remain unindustrialized and backward for the foreseeable future? And that is, in fact, what the projections show. There are efficiency improvements that are assumed in the models without scale. And anybody who studies efficiency, etc., in the industrial setup knows that there is a certain amount of scale at which you can achieve certain kinds of efficiency outcomes, which for smaller industries, for the informal sector, for small, medium sector, what we call the MSME sector, etc., those kinds of efficiency improvements are not possible. So how is it that, the developing world is assumed to achieve this? And then there are some things that are, of course, when models give these kinds of outcomes, then you have to also justify what happens. And so a lot of the food security concerns that have been raised were addressed in, one paper by saying that, okay, some of this can be addressed by everybody moving to Lancet diets by 2050. Now, Lancet diet is a particular kind of diet, which includes a lot of sort of non-meat. It's a non-meat diet. So a lot of the protein is met by nuts and, all kinds of exotic foods, which forget the poor in this country. Even for me to be able to afford on my salary on a long term for the entire family is going to be difficult. So these kinds of assumptions are embedded in the way in which models are done.
Tejal, you have another
Yes.
5 more minutes.
Yeah, I'm wrapping up. Last 2 slides. So this is, of course, all of this. So you have economic optimization, you have land use optimization, and then you have energy optimization, which is basically you look at the least cost solution globally to optimize energy use. So what you end up getting as an outcome is that it is cheaper to maintain poverty in the global south than reduce fossil fuel consumption in the global north. So it's much more expensive to reduce consumption of the rich. It's much cheaper to, there are cheaper options available. The poor are used to poverty anyway. So that becomes an ideological justification for this. Of course, nobody says it as blandly as that, but this is what the outcomes end up showing. So I want to sort of, I know that, a lot of you work on data training, earth system modeling, and are, buried in either the physical, looking at the physical constraints and the physical, boundary conditions, improving models, improving efficiency, improving predictions, projections. Precipitation is a big issue for all of us, and, especially for our region. All of these things are important. But, if you are, even if you're looking at those aspects of things, it is important to remember that some of these models feed into the earth system models that you work on. And there, it's not simply a question of whether you need better data training or whether you need better data solving capabilities or computational capabilities. That is really not the fundamental question. What we need to ask are the more fundamental questions about what is it that we are actually modeling, why are we modeling it, to answer what kinds of questions, and what are the approaches and why these approaches. So why optimize, for example? This entire idea that you need to optimize comes from an older way of building economic models. You have to find an equilibrium between supply and demand, for example, right? That was the thing that drove economic modeling at one point of time. And that seems to have percolated and continued into most of these other systems modeling that happens, where you are modeling the drivers of some of the changes that you might see in earth systems. So the fundamental question to ask is whether optimization itself is the right way to think about some of these issues. Then, of course, what the assumptions are. These assumptions and boundary conditions are unlike those in earth system models. They are, like I've said, subjective, they're normative in nature, and you need to be clear about the fact that they are normative. That doesn't mean that you should not have normative assumptions. Of course, the assumptions of, let's say, a projection of a more equal world is also a normative assumption. But then if you are clear that, in the social sciences, for example, something that is normative doesn't make it less scientific necessarily. It is just that you have to be clear about what those assumptions are, what they mean, where they come from, and the fact that there are other assumptions and other trajectories, other projections also possible. So there are inherent biases here that are involved and that you must be aware about. There are ethical considerations, at least the outcomes that you see from some of these models must make you stop and rethink the way in which you do those models. Unfortunately, there was, when we first published some of this work, there was a lot of pushback. Now, of course, there is some acknowledgement that this is a serious issue and this is not something that countries will simply accept as scientific outcomes. And the new IPCC 7th assessment cycle, for example, says very clearly that scenarios with sustainable development equity considerations must also be, assessed. So I will stop here and open for questions.
Okay, thank you, Tejal. Thank you for this insightful talk about like the policy implications of earth system models and integrated assessment models. The floor is now open for questions. Any questions? Yeah.
Hello, ma'am. I'm Dipan Chakraborty from IIT Kharagpur. So I have basically two questions. The first one is, does the model include some tricky conditions like war-like situation or well-known illegal mining in Mexico or Africa, their impact on the GDP and assessment? So this is my first question. And my second question is, do they give any kind of solution on kind of what we say neo-colonialism, Western oppression on Africa and Sahel region? Do they provide any kind of solution for that?
Yeah, so the answer to the first question is no. Discontinuities are very difficult to model in most of these kinds of models. You can have smaller subsets of models in some scenarios where you can do some kind of stochastic modeling where you can include discontinuities, but wars, etc., or even something like the pandemic, which constitutes a break in a trend, is much more difficult to manage. And issues such as which are much more localized in nature, like illegal mining, etc., are completely out of the ambit of the global models themselves. About the second question, I mean, the models in themselves are not supposed to provide solutions, either the IAMs or Earth system models. What they allow you to do, their use, and in fact, we must be very clear that they must be used for us to be able to check scenarios against each other, to see what happens if you do this versus what happens if you do that, what are the impacts on different variables. It's not about the provision of solutions per se. And solutions to something like neo-colonialism and imperialism is way outside the objectives of these models. In fact, if you look at some of the outcomes of the models themselves that I showed, you might wonder if the underlying philosophy is not the perpetuation of colonialism in some form, right? Because Africa is poor and remains poor for the rest of the century. It's almost as if the people of Africa have no aspirations to speak of, or those aspirations are not represented in the models at all. So in that sense, it is, so the answer to both your questions is no. But the second question is a little bit more, we must not think of, in fact, it would be dangerous to ask models to give the solutions to things like this. It would be like, it's my favorite example to give, the Hitchhiker's Guide to the Galaxy, where the problem to the solution to the problems of the world is just this one number, and nobody knows what that number means anymore after the computer spits out that number. So that's that's as much as I can answer that question.
Thank you, ma'am. Thank you.
Okay, any other questions? Yes.
Hello, can you hear me?
Yes.
Good morning. My name is Anirudh. It was an interesting talk. Definitely got me thinking a lot. But okay, it's in line with what was asked before, a little about solutions. So you have answered me a little, but how much of policy has been affected by these scenarios? Do we have any understanding of the change that what we've modeled has brought?
So it's see, if you look at policy actually gets implemented at a much more localized level, right? National, at the state level, at the national level, etc. What global scenarios do is they create a sort of international pressure point. And this has, to a certain extent, happened. If you look at, see, in the Earth system, in the physical science domain, they play a different role and an important role in at least, understanding how the climatic system is going to react to anthropogenic forcing. But here you're in the policy domain in terms of how is it that you change that forcing, right? That is where your focus really is. And if you say, okay, you have so much of a carbon budget, you have only so much space, or there's a range of trajectories beyond which you are in far more uncertainty. It provides a kind of a policy impetus to act faster, to try and find solutions, etc. So the pace at which things change is, of course, very slow. So you won't consider 30 years of change as very fast change. But They have had a certain impact, but not in terms of that I have designed my policy based on XYZ scenario, not in that sense. Correct. At the national level, of course, if you take some of these outcomes, for example, and say, okay, now let me do a national scenario. So Niti Aayog does, energy security scenarios. There are multiple people who work on energy models and things like that. The Central Electricity Authority itself works on it. They work on models with different levels of granularity. They work on models with different time horizons. Both temporal granularity is also very different, which make much more sense for more immediate planning. But they're informed by some of these. So, it's not directly visible, but given that the conversation happens, and there are other things as well, right? So one is we've been in a situation, let's say over the last 10 years, where targets are set from the top. And then the modeling community basically does scenarios to see how best to meet those targets. Now we are seeing a bit of a reverse trend where you're at least doing some of the modeling to be able to set better, more reasonable targets themselves. So in that sense, over a period of time, some of this conversation does evolve. It has an impact, but not a one-to-one impact. Like, this scenario will drive this kind of policy or things.
Thank you. Hello, ma'am. This is Rahul Kashyap. Thanks a lot for the insightful talk. Since India is the largest contributor to GHG emissions from Southeast Asia, being the largest country, so what are the land-based mitigation strategies to reduce or curb this land-based GHG emissions that you would suggest for future?
So one is, of course, India is not the largest emitter. Largest emitter in South Asia is not saying much, right? Between India, Pakistan, Nepal, Sri Lanka, Bhutan, India is the largest emitter. Okay, yes, true. But that's really not saying much, because if you look at globally, in absolute terms, yes, we are high, but in both in cumulative and per capita terms, we are not as high. But of course, India is a large economy. So in annual terms and absolute terms, we are the third largest emitter. So there is something that we need to think about. Land, of course, is a different question altogether, because land is a highly sensitive subject in India. One of the most important land-based, the only really proven at scale land-based mitigation measure is forestry. Right? But forests in India are not simply sinks for carbon dioxide emissions. They they serve as important, livelihood generation. People live there. People people cultivate in those lands. People have rights to, mine a forest produce. We have laws that protect people who live in forests. So there is a whole lot of there are a whole lot of issues involved there. And agriculture is another area where, of course, there is a lot of focus, which is mitigation centric. India's position, however, internationally has always been that agriculture is a sector which is important for adaptation. A large number of India's farmers are small and marginal, which is with very small land holdings. These are not this is not the section of the population that is responsible for emissions, and they should not be burdened by undertaking mitigation, by forcing mitigation on them. India is currently at very low levels. Our productivity, land productivity, agricultural productivity yields are extremely low as compared, even to comparable developing countries. I mean, you look at productivity, rice, wheat productivity in Vietnam as compared to India, India performs very badly in comparison. So a major focus in India has to be still has to be, in my opinion, food security, ensuring improved productivity and maintaining production given the impacts of climate change. Mitigation should be a focus for the industrial sector. Really. Let the farmers do their thing. That would be my opinion on this. But like I said, a lot of these issues are normative in nature. If I do the modeling of land, I'll do it very differently from the way in which some of it is being done today.
Hello, ma'am. I'm Deepak from IIT Roorkee. I have a question which was asked to me in a exam which I couldn't answer. So the question was that India has this goal of Vikshit Bharat by 2047, right? 2047. India has to be a developed country. That's the goal. So for achieving that, what would be a reasonable socio SSP scenario to be followed by the government and the people? This was a question, and we're asked to write an essay, and I would like some answers from you.
I mean, see, what does being a developed country mean? You have to first define the parameters for it. Right? Is it a certain level of income? Income is a proxy for a lot of things, but does it necessarily the content of that income, where that income is generated from, how it is distributed? All of these things would matter. Right. So if you look at parameters such as developmental parameters, and this is something that I work on with a student of mine. We've looked at 16 different development variables. If you say human development variables, you take life expectancy, mean years of schooling, primary enrollment rates. You take things like access to sanitation, access to clean drinking water, access to housing, a whole lot of these variables, and you look at where countries are situated. Right, India is somewhere in the bottom 20th percentile of countries, alongside a lot of countries of sub-Saharan Africa and countries like that. There are countries, of course, who are much, much higher than the norm, but a lot of countries, such at the upper middle income levels, also attain high levels of human development without necessarily extremely high levels of incomes. Incomes are driven by multiple things. So if you take a whole range of these kinds of variables and say your goal should actually, this is how I would address the issue. For me, developed country status or Vikasit Bharat would not simply be a certain amount of per capita income. Because per capita income will not tell me anything about the distribution of income. Right? India's mean income currently doesn't tell you how many people are actually below the poverty line. A couple of billionaires on one end skew the income distribution. So in that sense, what would be achieving a developed country status for me would be across all of these parameters in terms of housing, in terms of education, in terms of health, the access to healthcare, in terms of sanitation, water, all of these things. If you reach certain levels of well-being, for universal well-being, not just for some sections of the population, but for large majority of the population, if not all of them, then that would be achieving developed country status. But of course, if you ask somebody else, this is unlike if you go to a science department in ICTS, if you ask questions about things like, we all were discussing hydrostatic equations, right? You ask questions about the atmosphere, you ask questions about ocean, you might not get very different answers. You ask 3 different physicists, you're not going to get 3 very different answers. But the question that you ask 3 economists, you'll get 3 very, very different answers. That's the nature of the discipline itself. It's also the nature of the question itself. My idea of what constitutes development might not be the same as your idea of it. And that is why it has to be something that is subject to democratic decision making. It's not something that is simply, comes out of some kind of a technocratic understanding of development, but is a process which that is something that you arrive at through consensus, through democratic discussions across different sections of society. But we've gone far away from the modeling issue here.
Thank you, ma'am. I just got some answer.
Like I had one question related to the modeling issue here. So like you may be familiar with agent-based models where we actually try to represent the behavior of an individual and their interactions with the environment and so on. So I was wondering if in these energy models or these land use models, which vegetation dynamics models which you mentioned, like are these agent-based models somehow used, or is it done the modeling done in a different way?
So now there is an increasing number. There are agent-based models that are getting used. A lot of the localized land models do use agent-based models. So then there is an increasing influence of agent-based models, and in my view, they're probably a better way to go than the way in which current land-based modeling in the IAMs is done. A lot of the major IAMs, you take MACPI or Globiome, for example, these are large vegetation models. They are constructs of older, sort of older soil carbon sequestration models. But because they have to be coupled to the economic modules in the IAMs, they have sort of assumed a certain structure. But there are increasingly, there's an increasing number of agent-based simulation analytical models that, in my view, are far more useful, perhaps, and maybe eventually will be the way to go.
Thank you, Tejal. So, we are already way past time. So maybe if some other questions are there, in fact, I do have some. We will actually compile them and send you by mail. So maybe you can answer them later at your time. Okay.
Sure.
So thanks a lot. Thanks a lot,
Thank
Tejal. Let's thank the speaker.